Welcome to SciSense, where we unwrap scientific research, because science should not be a puzzle.
Welcome to the SciSense podcast. I'm Sarah, and I'm here with Mike. Today we're looking at the cosmos, and Mike, this one is genuinely poetic. Scientists have figured out how to find pairs of supermassive black holes by watching how they bend light from distant stars. This comes from a paper published in Physical Review Letters by physicists at the University of Oxford and the Max Planck Institute for Gravitational Physics.
Yeah, this is one of those studies where the idea is just beautiful. So let me set the stage. Most large galaxies, including our own Milky Way, have a supermassive black hole sitting right at their center. These are black holes millions or even billions of times heavier than our sun.
Okay, so one per galaxy. Where do pairs come from?
Great question. Galaxies actually crash into each other all the time in cosmic terms. When two galaxies merge, their central black holes eventually drift toward each other and start orbiting one another, like two dancers slowly spiraling closer together. We call that a binary, just meaning a pair.
And we've never actually confirmed one of these close pairs?
Not the close ones, no. We can spot pairs that are far apart, but the ones that are tightly orbiting, the ones about to merge, those have been invisible to us. And that's a huge gap, because those are the ones producing the strongest gravitational waves, which are ripples in the fabric of space itself.
So how does their method work? What's the trick?
It relies on something called gravitational lensing. Einstein showed us that anything with mass bends the space around it, and light follows those curves. Think of it like a bowling ball sitting on a trampoline. It creates a dip, and if you roll a marble nearby, the marble curves around the dip. Light does the same thing around a massive object like a black hole. The black hole acts like a giant magnifying glass in space.
Okay, so the black hole bends the light from things behind it. How does having two of them help?
This is the clever part. When you have two black holes orbiting each other, their combined gravity creates something called caustics. Now, the best way to think about caustics is actually something you've probably seen in real life. If you've ever looked at the bottom of a swimming pool on a sunny day, you see those bright, shimmering lines of concentrated light. Those are caustics, places where light gets focused intensely by the curved water surface. The two orbiting black holes do the same thing to Starlight, creating these invisible lines in space where light gets incredibly concentrated.
How concentrated are we talking?
Up to 1,000,000 times brighter. So, imagine a star behind this binary system. It's just a normal star, but an extremely hot and bright type called an O-type star. Think of it as one of the most powerful light bulbs the universe makes. When that star's light crosses one of these caustic lines, it gets magnified 1,000,000 times. For a brief moment, that single star shines as bright as an entire galaxy.
A single star as bright as a galaxy? That's insane.
And here's where it gets even better. Because the two black holes are orbiting, the caustic pattern rotates like a lighthouse beam sweeping across the sky. So background stars keep crossing these bright lines over and over. Each crossing creates a sharp spike in brightness. The researchers are calling this quasi-periodic lensed starlight, or QPLS.
So you'd see repeated flashes like a cosmic heartbeat?
That's a lovely way to put it. And the pattern of that heartbeat tells you everything about the pair. How quickly the flashes repeat tells you the orbital period, how long it takes the two black holes to go around each other. The brightness of each flash tells you how massive they are. The shape of the light curve tells you the shape of their orbit, whether it's circular or stretched out, which astronomers call eccentric, basically just meaning oval-shaped. And the angle we're viewing from, which astronomers call inclination, affects the pattern too.
So it's like reading someone's medical chart, but for black holes?
Exactly. All encoded in the timing and brightness of light flashes. And the numbers are really promising. Their models predict we could find between 1 and 50 of these systems, with the total rate of caustic crossings somewhere between 300 and 100,000 per year.
That sounds like a lot of potential discoveries. Do we have the telescopes to actually catch these?
We do, and it's perfect timing. The Vera C. Rubin Observatory, which is a massive new telescope being built in Chile, is designed to survey the entire visible sky every few nights. It will monitor around 20 billion galaxies. It is basically built for finding exactly this kind of repeating signal.
And I read there's a connection to gravitational waves too?
Yes, and this is where it all comes together beautifully. There's a space mission planned for the 2030s called LISA, which stands for the Laser Interferometer Space Antenna. It will detect gravitational waves, those ripples in space from merging supermassive black holes. But LISA works much better if you already know roughly where in the sky to look. So the light-based method could spot binary black holes years or even decades before they merge, giving LISA a head start, like giving someone directions to a house instead of making them search the whole city.
So one method feeds the other. Light finds them. Gravitational waves confirm them.
Exactly. Multi-messenger astronomy using different types of signals together. And one of the researchers, Miguel Zumalacárregui, said something that really stuck with me. He said supermassive black holes act as natural telescopes. The very things we're trying to find become the instruments that reveal themselves. The universe is quite literally helping us study it.
That gives me chills. So why should people care about finding pairs of black holes? What's the bigger picture?
It's about understanding how the universe is built. Galaxy mergers are one of the main ways galaxies grow and evolve. Every time two galaxies merge, their black holes eventually merge too, releasing more energy than anything else in the universe. Understanding this process tells us how the cosmos went from a simple, smooth beginning to the complex web of galaxies we see today. And on a philosophical level, the fact that we tiny humans on a small planet can detect events involving objects billions of times more massive than our sun, billions of light years away, that says something profound about the power of human curiosity and ingenuity.
Beautifully said, Mike. From swimming pool light patterns to the edges of the observable universe. Thanks for making that so clear.
Thank you, Sarah. And remember, everyone, science should not be a puzzle.
Thanks for listening to SciSense. Share it with a friend. See you next time.